Okay, next exercise 7. So we have come back to the problems on dual spaces. Here a vector space V is given which is finite dimensional and two subspaces W1 and W2 are given. We have to somehow describe the annihilator of the subspace W1 plus W2 in terms of the annihilator of W1 and the annihilator of W2. So let's see the solution. Since W1 is a subspace of W1 plus W2 and W2 is also a subspace of W1 plus W2, we have these two containments. The annihilator of W1 plus W2 is contained in the annihilator of W1 and it is also contained in the annihilator of W2, and this fact we have already seen before in a result in the text, that whenever you have two spaces related like this, their annihilators also have a containment relationship between them where the order gets reversed. Here W1 is contained in this, so the annihilator of this one is contained in the annihilator of this. So from these two things we can see that this annihilator is contained in, since it is contained in both of them, it would be contained in their intersection. This implies the annihilator of W1 plus W2 is contained in their intersection. We are now going to prove that the reverse inclusion is also true, and once we show that, these two things will be equal. So let F be any element in this intersection. Now, being in this intersection, F is in the annihilator of W1 and also in the annihilator of W2. So that means F makes any vector from W1 vanish, and also it makes the entire W2 vanish, in the sense that you take any vector from W1 or from W2, apply F on that vector, you are going to get the zero scalar. So we write then W1F is equal to 0 for all vectors W1 coming from W1, and like that W2F is equal to 0 for all vectors coming from W2. Hence, WF will be equal to 0 for all w belonging to this sum. Why? Because any vector in this sum is a vector in W1 plus a vector in W2. Now when you apply f to such a w and hence such a sum, say W1 plus W2, since f is a linear transformation, that will be equal to W1f plus W2f, both of which are 0, so their sum is 0. So that's how this is also 0. But then f belongs to what? F belongs to the annihilator of W1 plus W2. So what have we shown? An arbitrary linear functional, that is an arbitrary element in this intersection also is here. So this is contained in this, and that is the reverse inclusion. We thus have this A of W1 intersection A of W2 also contained in A of W1 plus W2. So this thing is the intersection of these two annihilators. That's how we have expressed this annihilator in terms of these two annihilators. And that of course is the end of the solution. And note carefully that although in the exercise it's given that the actual vector space is finite dimensional, we did not need that hypothesis anywhere. In fact, from the solution we can see that even if our vector space is infinite dimensional, still we have this fact. But it's given, so it's just there. The only fact in this solution that we have used, which is not a part of the solution, is that if two spaces, say U and V, are related like U is a subspace of V, then the annihilator of V is a subspace of the annihilator of U. So that is the only result we have used from the text. But in its proof, also finite dimensionality is not needed. It just comes directly from the definition of annihilator itself. So let's see the next one. The next one is also something similar. If again V is finite dimensional, and W1 and W2, just like before, they are subspaces of V. This time describe the annihilator of the intersection of these two subspaces. In terms of the annihilator of W1 and the annihilator of W2. And in this solution we would need finite dimensionality. So the beginning is somewhat like the previous solution itself, since this intersection is, let's write in words, is a subspace of both W1 and W2. We have A of W1 contained in the intersection, contained in the annihilator of the intersection, and like that this is also contained in the annihilator of the intersection. Hence, from these two things, it follows that I think it's we have taken sum, no? Yes. So this is a subspace of this. This is a subspace of this. The same thing. So the sum of these two will also naturally be a subspace of this, because of closure property, it's closed under addition of vectors. Hence, A of W1 plus A of W2 is a subspace of the annihilator of this thing. Okay. Now we are, now we cannot just simply show that the reverse inclusion is also true by taking an element from here. Maybe we can do that, but it's better to use, it's better to calculate the dimension of this sum, because things are finite dimensional, and before you do that, you have to make sure that all the spaces involved here are finite dimensional. How to make sure of that? See, it's given that our V is finite dimensional. So, the subspaces W1 and W2 themselves are finite dimensional being subspaces, and as a result, their annihilators are also finite dimensional. Or you can argue like this also, because V is finite dimensional, the dual space of V is also finite dimensional, and in fact they have the same dimension. Since A of W1, A of W2, these are subspaces of this dual space, so they are finite dimensional. Similarly, this one is also finite dimensional. Okay, so let us now start calculating the dimension. Now, so we calculate the dimension, we start our calculation by considering the dimension of this one. We can, however, if we want, consider the dimension of this one also, but let's just go the way I have gone here. Now, dimension of A of W1 plus A of W2. Okay, this is equal to, we already know the formula for this. This is equal to the dimension of A of W1 plus the dimension, I have space for this, A of W2 minus I hope I have not made a mistake here somewhere. Here, what I have written here. Let's see. So this plus this minus dimension of A of W1 intersection A of W2, and it's that formula that we have already seen quite a while ago when we were developing the theory of vector spaces and their dimensions. There we have seen this formula, the dimension of the sum of two subspaces. Okay, now things can be further there are other things that we can write in place of these quantities. For example, we know what this dimension is in terms of the dimension of W1, which is the dimension of V minus the dimension of W1. This is the dimension of the annihilator of W1, that means our first term, plus similarly this one is the dimension of V minus the dimension of W2 minus. Now note that in the previous exercise we have shown that this intersection is actually the annihilator of W1 plus W2. So we can use that fact here. This intersection is equal to this annihilator. If you want, you can write alongside that this comes from the previous exercise or previous solution rather. So this becomes 2 times the dimension of V minus dimension of W1 minus dimension of W2. Now this again can be decomposed, or we can write this in place of this dimension. Again, dimension of V minus dimension of W1 plus W2. So there is a little cancellation and we have dimension of V minus W1 minus W2. Okay, so this minus minus gives us plus. But now again we can simplify, I should not say simplify, but we can write the formula for this. Minus dimension of W1 minus dimension of W2 plus dimension of W1 plus dimension of W2 minus dimension of W1 intersection W2, in order to show that these last 3 terms come from this one. You can place them within brackets. Now you see that these things cancel out and you are left with dimension of V minus this, which again is equal to the dimension of the annihilator of W1 intersection W2. Hence, the annihilator of W1, or let me write like this, because we have been asked to express this in terms of the other two. This is equal to the annihilator of W1 plus the annihilator of W2, because we in the first part of this solution we showed that this sum is a subspace of this and all the spaces involved are finite dimensional. But then we started by calculating the dimension of this sum. It turns out that that is equal to the dimension of this. So this is a subspace of this and they have the same dimension, so they must be identical. Why? Because the dimension of any proper subspace of a finite dimensional vector space is less than the dimension of the original space. So we must have equality here, and that's just it. That is the solution. So here in this exercise we have in fact needed finite dimensionality, but we also had to use the previous exercise, for which however we do not necessarily need finite dimensionality. Next, if F is the field of real numbers, find the annihilator of W where there are two parts A. W is spanned by these two vectors. Spanned by these two vectors, one of them is this triple in 3D real space and the other is this triple 0, 4, minus 1, and part B likewise is this W is spanned by these four vectors from 4D real space, 1, minus 1, 2, 1, 1, 0 and 2, 1, 1, minus 1. Okay, so that means we are given two different vector spaces and two subspaces. Here the vector space in which we are having this subspace W is the vector space R3, and in this one the vector space is the 4D space R4 and the subspace is spanned by these three vectors. For such W's we have to find their annihilators. Okay. So we start off like this. Since the vectors one, 2, 3 and 0, 4, minus 1 are linearly independent, dimension of W is equal to 2. Since they are linearly independent, so W is two-dimensional because they form a basis for W. But why are they linearly independent? You can, if you want, you can consider a linear combination of these two, set that linear combination equal to the 0 vector 0, 0, 0 and show that the coefficient scalars are both 0. But there is a quicker way of seeing why they are linearly independent. You see, when two vectors are linearly dependent rather I should say, then one of them is a one of them is a scalar multiple of the other. Here, however, that is not possible. For example, had that been the case, this would have been some scalar lambda times this vector. However, no lambda will give you the first coordinate, because here the first coordinate is 0. No matter what you multiply 0 with, you are never going to get 1. So that is why they cannot be linearly dependent, and that's why they are linearly independent. So that's how we know that the dimension of W is 3. And from this dimension we will be able to calculate the dimension of the annihilator of W. Hence, the dimension of the annihilator of W is the dimension of V minus dimension of W. But what is V in this case? In this case, V is R3. In order to show that explicitly so that we do not get confused, this, the dimension of the 3D space is 3 and this one is 2, this is equal to 1. So in the dual space of R3, that's where this annihilator is a subspace, so it's a one-dimensional subspace. So it will be spanned by a single non-zero vector, that is a single non-zero linear functional in this, which of course belongs to the annihilator of W, not just any linear functional. Okay. Now, but how to find such a linear functional that will be in the annihilator of W? Now, let F1, F2, F3 be the dual bases or, in order to make it even more clear, dual basis of what? Dual basis of the dual space of R3. Oh, I wrote R, no? But in the exercise already it's given that F is the field of real numbers, so keeping up with that, let's write F3. Same thing, but you understand. It's the dual space F3 hat. It's a basis, dual basis of this space for the basis, for the standard ordered basis of R3, that is this thing, F3. Why do we need to consider the dual basis? That's because from this basis we will be able to write any linear functional, because this dual basis is a basis for the dual space. So any element in the dual space, that is any linear functional, will be a linear combination of these things. And we are going through the we are using this fact. That's because we know what these basis functions are precisely. Hence, any linear functional in F3 over F is of the form x1 f1 plus x2 f2 plus x3 f3, where x1, x2, x3 are real numbers. So that's how any linear functional looks. Okay, now we want a linear functional that will make the entirety of W vanish. Since W is spanned by these two vectors, it's enough to consider only those linear functionals, that is functions which look like this entire sum, that make these two vectors vanish, because then automatically all the other vectors in W will vanish. Why? Because if you apply this linear functional on this as well as on this and say the answers are both 0, then any vector in W is a linear combination of these two. So on that linear combination of, also if you apply such linear functional, that is also going to be 0, because the linear functional is a linear transformation. That's why. So that's why we write, we seek this. That is, if I won't be able to write it properly here, let me continue from here. That means if we apply our linear functional on this vector, that is on this vector we are applying this linear functional, then we should get 0, the 0 scalar. But this is the advantage of considering the dual basis, because we know what this thing is going to be, and it's going to be x1 plus 2x2 plus 3x3. To see why, you go back to this dual basis, that part, and then there you will understand. And also, what was the other vector? I forgot. 0, 4, minus 1. On that also we apply the functional, and we want to have the 0 scalar. and like the one above, here we will have 4x2 minus x3. So we now have a system of linear equations, a homogeneous system of linear equations in 3 unknowns, and we want to find these x1, x2 and x3, and because we want to have a non-zero linear functional, so we want a non-trivial solution to this system, and one such solution is what I have here. It is this: a solution to the above system of equations is x1 equal to minus 14. We just want to have a solution in which not all the 3 xi's are simultaneously 0. x2 is 1 and x3 is 4. So that's it. That means if we take minus 14 f1 plus f2 plus 4 f3, then that becomes the linear functional, and it will belong to the annihilator of w, because it makes both the basis vectors of w vanish. So automatically it makes the entirety of w vanish, and being a non-zero element in A of w, it will span the entire A of w, because in the beginning itself we have shown that A of w is one dimensional. So that's it. Now we can write so minus 14 f1 plus f2 plus 4 f3 belongs to A of w, and hence A of w is the linear span of the set consisting of this single linear functional. Okay, so that's just it. And now we know how to proceed with part B. And incidentally, here also the 4 vectors that are given are also linearly independent, just like the previous part. So we start off similarly, since the vectors, and here the vectors are 0, 0, 1, minus 1, then 2, 1, 1, 0, and 2, 1, 1, minus 1. Are linearly independent here. The dimension of w is 3, but the original space is 4 dimensional. Hence the dimension of the annihilator of w, here also it will be 1, because 4 minus 3, Having a one-dimensional space, it's easy to work with because every vector is a multiple of some fixed vector. It's like working in a cyclic group where there is a single generator. I should not say single generator, but a generator is there. All the elements are integral powers of that generator. So something similar happens in a one-dimensional space. Hence, this is equal to the dimension of this 4-dimensional real space minus dimension of W, that is 1. So, a single non-zero linear functional in F4 over F spans A of W, and the rest is similar. Let G1, because here we will have 4 vectors in the dual basis, be the dual basis of the dual space of the 4D space for the standard basis of the 4-dimensional space. Standard ordered basis, I should say. Of F4. Okay. Then any linear functional in F4 hat, that means any element in F4 hat is x1 g1 plus x2 g2 plus x3 g3 plus x4 g4, where the coefficients are real numbers. Again, we seek those linear functionals that will make our 3, 4 vectors that are given vanish. That is, it makes all of them vanish. So we seek zero, 0, 1, minus 1. And this turns out to be equal to x3 minus x4. Then 2110. And this becomes 2x1 plus x2 plus x3, and we will get one more equation. And that one, the vector is 2, 1, 1, minus 1. Oh, so we do not have any zero component here. 2, 1, 1, minus 1. And now again we seek a non-trivial solution to this homogeneous system of linear equations. And one such solution is here. We have x1 equal to 1, x2 equal to minus 2, and x3 and x4 equal to 0. We need at least one xi to be non-zero in order to have a non-zero linear functional. That's it. Some of them may be 0. We have this as a solution to the above system. Hence, so x1 and x2 are the only non-zero coefficients. That means g1 minus 2g2 is a non-zero linear functional that belongs to the annihilator of W. So in this case, A of W is spanned by this single linear functional. It's equal to the linear span of this singleton set. And that's where the solution ends. There are two more exercises in this set which we will solve in the next vector space update. And the next video today is what? Tuesday. So the next upload is on this coming Friday. And this Friday let's do calculus. While going through this kind of things, we often hear the word dimension, and we understand that it is a measure of how large the vector space is, but algebraically. However, when we think of the word dimension, something geometrical comes to our mind, and there are links, of course. Now one is perplexed by these 4-dimensional spaces, 5-dimensional spaces. We seem to be unable to geometrically think of them. Actually, we are unable to think of them because we have never encountered such objects. However, we can calculate about them, but how far are these things? I mean, just for the sake of calculation and just for the sake of doing mathematics, they look nice. But however, 4D geometry, 5D geometry, you may have heard about these things. If we are unable to think of, say, a 4D object or a 5D object, then does these, do these things make sense for the geometry? They make sense in a very specific way. In what way, I will discuss about that one day. You will realize that yes, they do make sense. Okay, someday let these things be over, and one day we will discuss about this higher dimensional things and geometries and how they are related to this notion of vector space dimension. This is not the only notion of dimension. There are others also. For example, topological dimension. Things like that are there. So we will see those things when we get the time and chance. So anyway, so see you on Friday with calculus. Until then, this is me, Lucifer, from a mathematical room. Have a nice night.